Today's topic is electric flux or represented by phi. Let's talk about the electric flux. It is defined as the number of electric lines of force crossing any cross-sectional area. Mathematically, it is given as the dot product of electric field vector and area vector. That is phi equal to so phi equals to E vector dot E a vector, where E is the electric field and A vector is the area vector, or equals to E a cos theta, where theta is the angle between area vector and electric field vector, or phi equal to E vector dot E dot A into n cap, where n cap is the unit vector along area vector. If this is represent area, and area vector is always perpendicular to the surface of the area. Here it is shown, and this makes angle theta with E vector because the electric field at this point is in this direction. So we can write A vector as A into magnitude into direction. N cap represents a unit vector perpendicular to the surface. So we have E vector dot E dot A into n cap, or A mod of E mod of n cap into cos theta. Now n cap is unit vector, so it will be 1. So A is cos theta. Since mod of n cap 1, n vector is a unit vector normal to the surface. Case 1, if theta equals to 0, then phi equals to, that is electric flux, Ea cos 0 equals to Ea. This is the case. This is the situation when theta is 0. That is area vector and electric field vector are along the same direction, or we can say that area surface is perpendicular to the direction of direction of electric field vector. Then this case will arise, and so we have Ea net flux equal to Ea, that is phi max equal to Ea. This will be the maximum value of flux. Now if case 2, if theta equal to 90 degree, this is the case. Here electric field is in this direction, but area vector is perpendicular to the direction of electric field, and this is the case for here. For example, this area is like this, and at this point electric field in this direction, so area will be perpendicular normal to the area surface area, so it will be perpendicular to the plane of the paper. So there will be 90 degree angle between area vector and E vector, and in this case phi will be a cos 90, and cos 90 is equal to 0. So flux will be phi minimum. Minimum flux, say in this case we obtain, and will be equal to 0. Now unit of phi flux, because phi equal to Ea, and E is electric field, so volt per coulomb, and area is meter square, so Newton meter square per coulomb. Electric field is Newton per coulomb, and area is meter square, so we can write unit of flux as Newton meter square per coulomb. And dimension is phi equal to Ea. So dimension will be dimension of E into dimension of A, dimension of E, dimension of A, and dimension of E we have calculated ml t minus 2 q minus 1 in MSKQ system, and area is L square, so we have ml3 t minus 2 q minus 1. Now in SI system, Q equals to dimension of Q is A into T, so we can write dimension of phi equals to m into LQ t to the power minus 2 a to the power minus 1, which comes out to be ml3 t minus 2 a minus 1 t minus 1. So this is the dimension for SI unit. Next, in elementary form, d phi equal to E vector dot dA vector. Here it is, so hence phi equal to integration of d phi or integration of E vector to dA vector, where E vector is electric field and dA vector is elemental area. If we have many surface, we divide surface into a number of surface like ds1, ds2 and ds3 and calculates electric fields for electric flux for every surface and then add up. So we can write phi equal to sigma all ei vector dot delta si vector. Also and this will add up to give integration E vector dot ds vector in continuous form. Now find the electric flux if E vector equal to 2 I cap plus 3 j cap plus 4 cap Newton per coulomb. And A vector equal to minus of 2 I cap plus 2 j cap plus 3 k cap meter square. Second, E vector is given minus 3 I cap 2 j cap minus 4 cap volt per meter, and A vector equals to I cap plus 2 j cap minus k cap meter square. So we have formula phi equal to E vector dot E vector, E vector dot A vector. So we can take dot product of these two vector 2 I cap plus 3 j cap 4 cap dot minus of 2 I cap plus 2 j cap plus 3 k cap. So 2 into minus 2, this will be minus 4. And 3 into 2, 6, and 4 into 3, 12. So will be, after calculating, we get 14 Newton meter square per coulomb flux of this area. And again in second, again taking dot product, we get 5 volt per meter or Newton meter square per coulomb. Next, direction of area vector is from surface toward us and perpendicular to the plane. For example, if this is a perpendicular surface, consider, and if this surface is perpendicular to the plane of the copy or plane of the board, then, and if we see this surface, like this surface is like this, and if see from this side, then area vector will be, the direction of area vector will be towards our eyes or towards us. Again, if we see from this side, that is from left side, then area vector will be towards our eyes or towards us. So A cap will be A into N cap, where N cap is in this direction for this case, and N cap is for this direction for this case. So the direction depends on how we look the area or how we see the area. Next, for a closed body, outward flux is taken to be positive while inward flux is negative. For example, here a positive charge is placed and it is surrounded by a spherical surface area. So because flux electric field is in outward direction, radially outward direction, so this flux will be called positive because it is outward flux. So we take it as a positive, while in this case here this is a closed surface and electric field is like this going towards this body, inside the body. So this will be negative flux. For example, here it can be easily understood. Here a minus q charge is placed, then electric field lines will be in this direction towards the charge. So in this case, area, because we are seeing outside this surface, so area vector will be perpendicular to the surface toward us, but electric field is towards the center. So in this case theta is 180 degrees, so phi is negative, that is electric flux is negative. Here a case of uniform electric field is shown and a closed cylinder is placed, hollow cylinder. Then we have to find, or maybe solid cylinder, solid cylinder, it don't matter. So in this case electric field is like this. So here, because this surface, we are looking this surface from this side, so electric field and area vector is same direction, that is n cap, unit of area vector in same direction. So flux through this curved surface, this circular surface will be positive, and here n cap is in this direction and area vector is in this direction. So flux in this case, flux of this surface area will be negative, or given by phi equal to minus of pi r square into E, because area is pi r square and electric field strength is E. Now from the curved surface, because every point on the curved surface, electric field is parallel to the surface and area vector is perpendicular to the surface. So here theta is 90 degree. So flux of this curved surface will be 0, phi, because theta equal to 90 degrees. So curved surface flux is 0. So this is the case for a hollow cylinder placed with the electric field. So we can write total flux phi E net equal to phi E left surface ls plus phi E curved, this surface is curved, and phi E right surface equal to 0, because adding these three flux we find 0. That is, from this we find a important point, that if a closed body not enclosing any charge is placed in an electric field, either uniform or non-uniform, total flux linked with it will be 0. So it means that if we placed a closed body inside the electric field, the flux through it will be 0. It means that no electric field lines pass through the inside the body. For in this case example, and in this case, because there is no lines of force passing through the body. Again in this case, no lines of force will pass through the body, and so phi will be 0.